So on the top we have our inputs, right? 0 through 27 and 17. And then we have our outputs right here, right? So what we have is, you can see 4 and 5 are illuminated, 22 is illuminated, right? And so if you were ever to troubleshoot the system, or find out what's going on with it, how you would do that was what you do is, okay, so now what you do is you just go in here, right? And you can see right down here, right? Okay. Sump level open, X7. Sump level close, X10, right? So you can just go through this print, right? And you can find out pump pressure switch on is okay, right? So let's see. X17, input 17. Input 17 is off, right? There's no light inlet on there. So that means that the pressure switch has not been made, most likely because the pump hasn't turned on, right? So when we turn the pump on, we should expect to see light 17 going up. That's just one example. So if you're ever getting alarms or something like that you can't explain, understanding what the lights on the PLC mean is a real good way of understanding it. Okay, so now when you're looking here, it's kind of difficult to see, but you've got X4 lines up exactly with that's output X4 right up there, and then X5 lines up right here, right? So you can see when you're reading these numbers, it's kind of difficult to see, but that's how they actually work. So if you ever had to do it, it would be there. All right. So now what we've got here is this breaker is for the motor start. It's got an overcurrent, and this one's just for the electronics in the system. This is the motor contactor. So when I hit that, then the motor actually starts spinning. You've got a 24-volt power supply. You've got different relays, and I'd have to look at the prints to know exactly which relays for what, but different relays that actually actuate the valves and everything else in the system. This is the phase rotation detector. Are you guys familiar with those? So it's only really useful in the when you first start up the system, but this is a three-phase system, so the actual rotation of the order on which the voltage comes on each phase actually affects the direction that the pump is actually rotating. So, yes, sir.
No, Doctor. Sir, is this recording? Yeah, no, this recording. This is recording, and don't stop in between unless you really need to.
Yeah. All right. Okay, so. All right.
We're actually supposed to be butters. You, and that might say you and Umesh, you both are using series.
Yeah.
Okay. They use it to be present. And I don't know.
So can I be here? I just need to learn the system, but I won't be using the system.
We like to copy the matter. Or I will. For the rest of you guys, it's up to you. If you want to stay around, fine. Otherwise.
Okay. I'm going to just do my best I can to teach these guys what it does and why. And
can you start with the overview of the system? What
yeah. Well, do we have a whiteboard or something like that?
We have upstairs.
Upstairs.
Yeah.
Before we start this system up, they need to fix that water leak, otherwise we'll be swimming in about 5 minutes, right? Okay. Yeah, we had a plumbing leak right there. Okay. On that fitting, and I can't tighten it up tight enough with my hand. Okay. But other than that, we can go upstairs, spend 10 minutes with an overview of the system,
and come back.
And then come back down here. Okay. And I know he needs to get out of here a little bit earlier, and you can be here for as long until I bore you to death. Okay. All right. Ones that we were worried about, plus elemental sulfur, which we don't care so much about. And so now coming into the wet scrubber, right? you're going to have silicon tetrafluoride, and that's going to react or become absorbed into the water, right? So then, inside this wet scrubber, you've got, in the process, you've got sulfur hexafluoride, is broken apart by an RF, and it actually makes silicon tetrafluoride when it actually, because you're trying to clean the silicon out of the chamber, right? And then that's a byproduct of inside your reaction, and the scrubber is going to actually become part of the water. I'm not a chemist, so please, any of the chemists correct me when I make a mistake. And plus the fluorine is also soluble in water, and it's going to be going in there. So now the reason I'm talking about this is because when you're doing maintenance on this system, you should be aware that there are going to be low levels of fluorinated compounds inside the water, right? So you need to take proper PPE, right? So the minimum is going to be your gloves, and you're going to have to take care not to get the water on your skin or such like that, right, when you're actually performing maintenance on it. Silane, okay? So silane, you're going to have small concentrations of silane going into the scrubber. And we talked about already, we have the stage 1 and stage 2 of the CDA addition. That provides the oxygen for your reaction. So you're going to have, and we're going to show this in just a little bit. I'll actually draw a picture inside of the entry. And so what we're going to have is the oxygen is going to react with the silane, and it's going to make silicon dioxide and water. All right. So nobody cares about the water. The silicon dioxide is going to be the white powder that you're going to find inside your pipes and your CVD, everything, everywhere inside there. Okay, the diborane, I'm not sure what the reaction is on that. Whoever the chemist is going to have to cover that. The phosphine is air reactive also, right? And so it'll create some oxide of phosphorus plus water, right? CH4 will probably pass through the system without being reacted at all and come out your exhaust diluted, all right? Okay, so now, I'm going to go ahead and go to the next page. Oops.
Just click new page.
Oops. Thank you, sir. I'm sorry. All right, so now.
One quick question, actually.
Yes, sir.
Sorry. We also have SF6 for the cleaning purpose.
Yes, sir.
And probably it wouldn't react with water at all because it's very,
Yes, that will. If it's not broken apart by the RF inside your chamber, whatever the SF6 will pass through it absolutely untouched through that system. Correct.
Okay, basically we use plasma on SF6, so it will be probably reactive. Okay.
Yeah, you're going to be. I'm going to guess. I don't know your specific chamber, but somewhere in the neighborhood of 60 to 99% is what the other chambers that I'm familiar with. Right. The least efficient being 60. The most efficient would be a 99% dissociation of the sulfur hexafluoride.
Sorry, I didn't get that.
That's the amount of sulfur hexafluoride that will be coming out and going out your exhaust stack is dependent on the efficiency of the RF clean. And the least that I've heard about is the lowest efficiency that I've heard about is about a 60% efficiency, and the highest Applied Materials claims not over 99% efficiency on their sulfur on their RF chamber.
We were also thinking of using NF3, nitrogen and basically NF3 instead of SF6.
Correct.
And I basically, the chemistry of that, I'm not sure how would it react with water,
NF3 will pass through a scrubber unmolested, unless you have a different type of scrubber with a burn, like a hydrogen, such as a Guardian or something like that, or that will actually break down a small amount of the, or some portion of the NF3, depending on the process. However, the nitrogen trifluoride will pass through this scrubber unmolested. It will go past, whatever goes in will come out in full force. However, NF3 has become popular in industry lately because it has a much lower half-life in the atmosphere than, say, sulfur hexafluoride or C3F8 or something like that. Whereas I'm just guessing at the numbers, but 1 ton of C3F8 is, I believe, equivalent to 10,000 tons or 50.